This is a very short video on acid-base titrations and how to calculate the unknown concentration in molarity of an acid or base. So in a titration, you have an unknown substance. Well, you typically know what the substance is, but it contains an acid or a base with a concentration that is unknown. And so you titrate or react it with a known concentration of a known substance that you know will react with it. So, for example, let's just say the unknown was an acid and that we wanted to know the molarity of the acid in there. So you might get a sample of pond water or something, okay? And then you take a known concentration of some base, we'll just say, for example, sodium hydroxide, and you add it through a burette, which is a very precise volumetric container, and you add it dropwise, and you know acids and base react, and you use the stoichiometry to figure out how much of the known substance it takes to completely react with the unknown. And then you use stoichiometry, and you can figure out the concentration of the unknown. There are several different types of titration, but we're just going to talk about acid-base titration. Okay, so remember, an acid is something that donates or provides a hydrogen ion in solution, and a base is something that produces a hydroxide ion in aqueous solution to produce a salt, some type of ionic compound, and water. The equivalence point is the point when you're doing a titration at which all of the substance that you're analyzing, so the analyte, when it's all been reacted, okay? In other words, when enough of the titrant, that's the stuff that's in the burette, when enough of the titrant has been added to completely react the analyte, that is considered the equivalence point. And so being an acid-base titration, at the equivalence point, you would expect it to be neutral, okay? The point when you have neutralized all of the unknown acid with a base, or vice versa. All right, so let's talk about really the purpose of this short lecture, and that is, what is the math, or how do you figure out the concentration of an unknown acid or base from a titration? So the best way to teach it, as always, is to go through an example. In an example, you will always be given the volume and the concentration, molarity, of the known substance, okay, the titrant, the stuff in the burette, okay? And you will be given only the volume of the analyte, or the unknown, because you're trying to figure out the molarity of the unknown, right? So we are going to base this entire calculation on the fact that at the equivalence point, the moles of acid added, and moles of hydronium ion added, equal the moles of hydroxide that were there, okay? Equal moles, okay, means neutral. That's the equivalence point. But basically, the moles of acid equal the moles of base. Now, do we remember how to get moles using molarity? When we talked about our molarity, I'm just going to remind you of the formula. Oops. Molarity equals moles over liter. And so to get moles, if we rearrange that equation, moles equals molarity times liter. All right, so we're going to start by doing that. We're going to figure out the moles of the known. So we're going to convert the milliliters to liters. We were given 12.15 milliliters. And so that's our volume. We're going to multiply that by the given molarity of the known, the titrant, 1.885. And that will give us the moles of the sodium hydroxide that were required to reach the equivalence point. Okay, moles of titrant required to reach the equivalence point. So it means that that is the same number of moles of the acid or hydronium ion, right, that had to be neutralized in the Erlenmeyer flask. So just to show the formality, we calculated, that was my dog drinking water in the background, by the way. We just calculated, right, that 0.02290 moles of the base were required to reach the equivalence point. We know that according to the balanced equation, which is up here, there's a 1-to-1 to 1-to-1 ratio here. In other words, for every one base, there's one acid. Okay, that won't always be the case, so be careful to look back at the balanced reaction and have the correct mole ratio. And so in this case, we have exactly the same number of moles of the acid that we're trying to analyze. All right, so now that we have moles of the acid, how do we get molarity of the acid? Okay, remember, molarity is moles divided by liter. Okay, we know moles, so we need the volume that the acid took up. The problem gave that, see? Problem gave the volume. So the molarity of the unknown concentration of acid is 0.02290 moles divided by, and again, I converted the milliliters to liters, 0.025 liters. So the concentration of the unknown acid is 0.92 molar. Now that I showed you the methodical way, because I wanted you to understand why we are calculating it that way, I'm going to give you a shortcut now, so you can end up doing the calculation either way. All right, this is the same problem. I just repeat it up here in case you want to read it again. Okay, and then you always want to start by writing a balanced reaction for the titration if it's not provided for you. Remember how I told you at the equivalence point that the moles of acid equal the moles of base. And that's only at the equivalence point, right? All right, so let me just specify equivalence point. Well, another way of stating that equivalency is we know that moles is molarity times volume, right? So another way of stating moles of acid equals moles of base is molarity times volume of acid equals molarity times volume of base. So here's the magic shortcut equation, again, that can only be used at the equivalence point. That looks very familiar to the dilution formula, doesn't it? There's one little difference. I don't know why I have the Na out here, rats. Notice these little n values. The dilution equation, just to kind of remind you, was this, right? So it almost looks like we just replaced, instead of the 1 and 2, we replaced it with A and B, but there's one more difference, and that's these n values, okay? And pay close attention, because it's a very common error. Oh my gosh, I had these mixed up. Shoot, sorry about that. All the acids go together and all the bases go together. All the B's go together, all the A's go together. All right, so Na is the number of hydrogen ions in one molecule of the acid. So if I had HCl, one molecule of HCl has one hydrogen ion. All right, so Na for that would be 1. If I had H2SO4, the number of hydrogen atoms per one molecule of H2SO4 is 2. All right, so basically these N values represent the mole ratio that you would use if you were doing the original way, the long stoichiometry way. And so NB is a similar thing, okay? It's the number of hydroxides in one molecule of the base. So again, if you had sodium hydroxide, and B would equal 1. If you had magnesium hydroxide, and B would equal 2. Okay. Alrighty, so just to kind of prove to you, you get the same answer regardless of the way you do it. Since we are working with acetic acid and sodium hydroxide, Na and B are both 1. That's what these ones are. We're trying to solve for the molarity of the acid. We know we have 25 milliliters of acid. So these are all givens, okay? Here's the molarity of the base. It was given. Here's milliliters of base used. And what I love about this formula, as well as the dilution formula, is it does not matter the units of the volume, okay? If you're just solving for simple molarity, you want liters in that equation. But since this has volume on both sides, the units are going to cancel. So as long as you use the same units on both sides, you're perfectly fine. So again, solving then for the molarity of the unknown acid, we get the exact same answer we did doing it the longer way. Here is one for you to try. So just kind of a hint, I'll get you started a little bit, okay? If you're in Dr. Maffei's in my class, you're going to want to go formative and work this one out. But the balanced reaction, and you should know how to convert names to formulas, particularly for the final exam coming up. So that's something you want to refresh your memory. But for now, I'll just go ahead and help you with it. Sulfuric acid is H2SO4. And it is reacting with sodium hydroxide. It's important to balance the reaction also. Water is always one of the products, and the other is a salt or ionic compound from what's left over. So you want to look at the cation and anion from the acid and base and combine them. But before you write a formula, as with every single ionic compound, you need to assign common charges and crisscross so that your formula overall is neutral. So the formula for the salt is Na2SO4, sodium sulfate. All right, so once you have the products, you want to go ahead and balance the reaction. So I'm going to put a 2 in front of the sodium hydroxide, trying to balance my sodium, my metals. The sulfate, the polyatomics are balanced. There's 1 on each side. And I'm going to go ahead and balance hydrogen and oxygen now. There are 2 plus 2, 4 hydrogen on the reactant side, so I need to put a 2 in front of water. So there's the balance titration, and now you should be able to, I would try it both the conventional stoichiometry method as well as the shortcut method, and just double check your answer and get experience with both methods. That's it for this PowerPoint.